a plus x power n. This a plus x power n, when we expand, is going to be what? A power n plus nc1 a power n minus 1 x nc2 a power n minus 2 x squared nc3 a power n minus 3 x cubed, and so on and so forth up to n plus 1 terms. 1 more than the power would be the number of terms, right? Isn't it? The r plus 1th term in this expansion, the r plus 1th term in this expansion is going to be NCR a power n minus r x power r. R equal to 0 will give me the first term, r equal to 1 will give me the second term, r equal to 2 will give me the third term, r equal to n will give me the n plus 1th term, right? So when I vary r from 0 all the way to n, I get all the terms. I get all the terms. Yes or no? Now, different powers of x will have different supporting coefficients, right? I want to find the power of x whose total coefficient would be the maximum, the term which is the largest in number, the term which is the large. See, if I give different values to a and x, then different terms will have different values, isn't it? Yes. The first term will have a value whatever a to power n, the second term will have a value nc1 a to power n minus 1, that value of a, that value of x. Different terms will have different values. I want to find in this collection of n plus 1 elements the term that has the greatest value. Numerically the greatest value. That means I want to find the numerically the magnitude of the greatest term. Magnitude of the greatest term. See, because x and a could be negative, right? Say if x is negative and a is positive, then this will be a positive term, this will be a negative term, this will be a positive term, that will be a negative terms. Terms will alternate between positive and negative values. But every term will have a numerical value. I want to find the term with the largest numerical value in this collection of n plus 1 terms. Given the value of x, given the value of a, I want to find, I am seeking to find the term whose numerical value mod of that would be the largest in this available sequence. That's a problem to address. That's a problem to address. Now what we do is, I start by comparing consecutive terms. In the sense, you know, my terms are like the t1 the first term, t2 the second term, t3 the third term, tn plus 1 the nth term. Now the whole blueprint revolves around the following. Let me compare a term with its previous term. Let me compare a term with its previous term. This is a term. The previous term would be tr, isn't it? That means I am comparing neighboring terms. I am comparing neighboring terms. tr would be what? ncr a to power n minus r minus 1 x power r minus 1, isn't it? Right. Isn't it? Now, what I might end up getting is, let's say, when I compare terms, I find that up to a certain value of r, the next term is bigger than the previous term. That means terms are increasing. And then, for a certain value of r, the switchover takes place. The terms start to decrease. See, what might happen is, the terms start to increase at a certain value of r, and then terms start to decrease when I compare neighboring terms, right? And then I know then that there is a maximum term available somewhere here. It's first increasing and then decreasing. Let me figure out the behavior of a term with respect to its previous term first, so that I can qualitatively and quantitatively analyze whether the sequence TR is a sequence, whether that TR sequence is increasing, decreasing, up to what value of R is it increasing, and then after what value of R is it decreasing. Then that will help me understand the trend of the values that these terms assume. You realize what I'm trying to do here? Right, so I'm aiming to compare consecutive terms. Any term divided by its previous term, isn't it? This is any term divided by its previous term. Now, TR plus 1 divided by TR. This is any term divided by its previous term. Please check for yourself that this is n minus r plus 1 into x by a. I want you to be able to verify the authenticity of this. Will not be rocket science to do that, isn't it? X by a is all right, and NCR by NCR minus 1 would actually be n minus r plus 1 by r. If you divide NCR by NCR minus 1, that's going to be n minus r plus 1 divided by r. Yes or no? When I talk of the numerical ratio of two terms, then mod TR plus 1 by mod TR. See, this anyways is positive, so this you can leave out, mod x by a. Yes or no? Yes, ratio of any term by previous term, numerical ratio of a term divided by, numerical ratio of a term divided by its previous term would be this. Yes or no? Yes. Right? Now, instead of giving you sermons, let me tell you the two kinds of things that you would encounter when you compare terms, and refer to problems 1 and 2, part 1 and 2 of the first problem of the sheet titled Binomial Basics. I will use that as a mouthpiece to deliver my idea here, right? This you should remember, ratio, numerical ratio of two terms, consecutive terms next to previous would be n minus r plus 1 divided by mod x by a, right? Now, look, this problem, 2 plus 3x to the power 10, when I expand this, it will give me 11 terms. It will give me 11 terms. I want to find the term which is numerically the greatest. The term which is numerically the greatest. So, this, for, in this case, a is 2, right? We want to find this for x, and instead of x, you have 3x. Instead of x, you have 3x. We want to find numerically the greatest term for x equal to 3 by 5. For x equal to 3 by 5, I want to find which of the 11 terms will be the greatest in this expansion. Clear? Now, TR plus 1 by TR, numerical ratio of two terms. In this case, R is 10, A is 2, and x would be 3 into x. That means 9 by 5 would be x, isn't it? Instead of x, you have 3 into x, which is 9 by 5. That's 9 by 5, right? So that's like a n, which is 10 minus r plus 1, isn't it? N minus r plus 1 divided by r into magnitude of 3x. 3x is 9 by 5. So by a, so 9 by 10, isn't it? 3x by 2, isn't it? See? 3x by 2. So 9 by 10? Clear? Now, let's see up to what extent next term would be larger than the previous term. So next term would be larger than the previous term when this is greater than or equal to 1. Then the next term would be not smaller than the previous term, at least, isn't it? Because this is ratio of, numerical ratio of next term by previous term. For a certain value of r, next term would not be smaller than the previous term. This is what this statement means. Yes or no? This is the meaning of the statement. Clear? Now, this is 9 into 11 minus r. 9 into 11 minus r greater than or equal to 10r. Up to such an r, this is going to happen. Next term will be larger than the, greater than or equal to the previous term up to this value of r. Up to r satisfying this condition. That means up to what r? This is like 19r less than or equal to 99. Up to such a value of r, this is going to happen, right? That means this will happen for r less than or equal to 99 by 19. Yes or no? Which is like 5 point something? Which is like 5 point something? Yes or no? Now let's investigate. But so far so good, right? Now must tell you that for r equal to 5 point something, for r equal to this value, tr plus 1 would have been equal to tr. Mod tr plus 1 would have been equal to mod tr, isn't it? See, when r becomes equal to this, this becomes equal to this, this becomes equal to this, then mod tr plus 1 will become equal to mod tr, isn't it? If r could assume a value 5 point something, then for that value of r, these two neighboring terms would have been the same. For a value of r which is 5 point something, for a value of r which is equal to 5 point something, mod tr plus 1 would have been equal to mod tr. Next term would have been equal to the previous term. Hey, but watch out. R has discrete values only. The values that r can assume is 0, 1, 2, in this case up to 10, 11 terms, r will assume values from 0 to 10. Is r ever assuming a value equal to 5 point something? R is never assuming a value equal to 5 point something. That means if r never assumes a value equal to 5 point something, that means tr plus 1 can never be equal to tr, right? That means this can, because r is never assuming this value, then no two terms in this expansion will ever be the same. No two neighboring terms will be the same, I mean. No two neighboring terms will ever be the same for any value of r, because the only possible value of r for which a term could have been equal to the previous term numerically is 5 point something. But r is never assuming non-integral values here, right? So now, let me then figure out what then is the maximum or the numerically the greatest term. What is established is that no two neighboring terms are equal, because for them to have been equal, then r should have assumed a value 5 point something, then t 5 point something would have been equal to t, I mean this is t 6 point something would have been equal to t 5 point something, but there is nothing like a t 5 point something, isn't it? So what is the maximum value of r for which next term will be greater than the previous term? 5. So can I say that if r is less than 5 point something, that means r less than or equal to 5 point something, right? For r less than 5 point something, say 5 point something, tr plus 1 will be equal to, will be greater than tr. Yes or no? Do you understand this? You know what I'm saying here? See, in this case, r equal to 0, 1, 2, 3, 4, 5. Up to r equal to 5, tr plus 1 is necessarily bigger than tr numerically. Yes or no? This is what it means. Are you confused? From r equal to 0, 1, 2 up to 5, next term will be necessarily larger than the previous term, right? That means for r up to 5, next term numerically is bigger than the previous term. That means, say the first term is t1, would be numerically less than t2. This is r equal to 0. This is r equal to 1, right? t3. For r equal to 5, you have t6. Yes or no? This is r equal to 0, this is r equal to 1, this is r equal to 2, this is r equal to 3. So previous term will be smaller than the next term. For r equal to 0 all the way to 5, previous term will be smaller than next term. Yes or no? Up to r equal to 5. No, didn't understand this? Okay. See, in this case, for r equal to 5 point something, next term would have been equal to previous term. But r is never assuming a value equal to 5 point something. R is always less than, r will at best be equal to 5. Now when r is 5, then the equality will not occur. That means mod tr plus 1 will never become equal to tr, mod tr. That means mod tr plus 1 will be larger than mod tr up to r equal to 5. Up to r equal to 5, up to r equal to 5, mod tr plus 1 will be larger than mod tr and never equal to mod tr, right? This is what, so r equal to 0, mod t1, previous term less than next term. This is now the previous term less than next term. And this entire thing, previous term less than next term, happens all the way to r equal to 5. R equal to 5 will be t6. The sixth term, yes or no? R equal to 5 will be the sixth term, right? Now, so far so good, right? So when you go from the first term to the sixth term, the sequence tr is increasing. When you go from the first term to the sixth term, the sequence is increasing, right? Now, after this, but I hope you are all in sync with me, right? Now, after this, for r greater than 5 point something, that means r greater than or equal to 6. See, up to this it's decreasing. For r equal to 6 onwards, if r was less than or equal to this, it will decrease. But if r was greater than or equal to this, then the sequence will be increasing. Yes or no? See, if I had, say, next term less than the previous term, see, that means this would have been less than or equal to 1. This is next term, by previous term would have been less than or equal to 1. So I'm trying to identify the range of r over which the sequence is decreasing. So next term by previous term would have been, this would have been less than or equal to 1. This would have been less than or equal to 10r. This would have been less than or this would have been, sorry, less than or equal to 10r. This would have been greater than or equal to 99. This would have been r greater than or equal to 5 point something. So, isn't it? So mod tr plus 1 would have been greater than or equal to mod tr for r greater than or equal to 5 point something, right? And r equal to 5 point something, mod tr plus 1 would have been equal to mod tr, but r is never becoming equal to 5 point something, right? That means mod tr plus 1 is never becoming equal to mod tr. That means mod t, for eventually I have to say r greater than or equal to 6. Mod tr plus 1 will be greater than mod tr. Mod tr plus 1, sorry, less than, all of this was less than only, on that premise only. Mod tr plus 1 by mod tr less than or equal to 1. That means mod tr plus 1 less than mod tr. Why is mod tr plus 1 never becoming equal to mod tr? Because r is never becoming equal to this. Hey, one thing, up to this value of r, the sequence is decreasing. That means after this, the sequence must be increasing only. I'm sorry, up to r equal to this, the sequence is increasing. That means beyond this value of r, the sequence must be decreasing. You expect that to happen, right? Because we found the range of r for which the sequence is increasing. Up to r equal to 5, it's increasing. From r equal to 5 onwards, it will be decreasing. That's what it means. That means for r greater than or equal to 6, mod tr plus 1 will be less than mod tr. Mod tr plus 1 would be less than mod tr. That means this is r equal to 6, mod t6 will be greater than mod t7. R equal to 6, mod t6 will be greater than mod t7. So this is mod t6. This will be, so this is mod t1 less than mod t2 less than mod t3 less than mod t6, and mod t6 r equal to 6, mod t6 will be greater than mod t7, right? R equal to 7, mod t7 will be greater than mod T8. Similarly, greater than mod T9, etc. So what is happening? If you are going this way, it's increasing up to the sixth term. Up to the sixth term, it's increasing. And after this, from this point onwards, it's dipping. That means what's the largest term? T6. It's larger than all terms to the left of it and also larger than all terms to the right of it. That means mod T6 is the largest term. Mod T6 is the largest term. Yes or no? Right? And that happens for r equal to 5. That happens for r equal to 5. Have I confused you or are you fine with this? So, what is T6 then? T6 is T r plus 1, which is NC, in this case 10C 5, a to the power 5, 3x to the power, in this case a is 2 to the power 5 into 3x to the power 5. Plug in x equal to 3 by 5, that will be the greatest term. This is 10C5 a to the power n minus r, and then 9 by 5 to the power 5. That's numerically the greatest term, and it's the sixth term. Its numerical value will be the largest. The numerical value of the sixth term would be the largest it could be. Has this settled in your heads? Right? Now, see, another variation to this. If you finish copying, let me move on. Part 2, 3 minus 5x to the power 15 for x equal to 1 by 5. There will be 16 terms in the expansion of this, and the signs will alternate. The signs will alternate, isn't it? Because of the minus in between. We want to find numerically the greatest term. We want to find numerically the greatest term in this. Clear? Now, look, like before, magnitude of next term by previous term. Magnitude of next term divided by previous term. N minus r plus 1 divided by r. N is 5 here. 15. 15 minus r plus 1 divided by r, right, into magnitude of minus 5x by 3. Magnitude of minus 5x by 3 would be the numerical ratio of next term to previous term. Next term to previous term. That's a numerical ratio, right? Put x equal to 1 by 5. So this is like a 15 minus r plus 1 divided by r into 1 by 3. Into 1 by 3. Let me find out the range of r for which the next term will be larger than the previous term. Mod na? Numerical ratio of two terms. I want to find numerically the greatest term in the expansion of this. Right? Now, when would the next term be not smaller than the previous term? If this ratio is greater than or equal to 1. Clear? That means this would be the range for which the next term will be numerically not smaller than the previous term. This will give me the range of r for which the next term will not be numerically smaller than the previous term, right? This happens when 15 minus r plus 1 is greater than or equal to 3r. That means this happens when 4r is less than or equal to 16. This happens when r is less than or equal to 4. Yes or no? Yes. And when r is equal to 4, for r is equal to 4, this ratio will become equal to 1. Isn't it? That means mod tr plus 1, that means t4 plus 1 tr plus 1 must be equal to mod tr. That means the numerical ratio, numerically the fifth term and the fourth term would be equal numerically. Numerically the fifth term and the fourth term will be equal, right? Okay, now let me lay it out for you. See, r equal to 0, 1, 2, 3, 4, right? R equal to 0 will give me the first term, tr plus 1, mod t2, mod t3, mod t4, mod t5, right? So this is up to r equal to 4, and this mod t4 is the same as mod t5, right? But other than this equality, next term has always been larger than the previous term up to this point, except for this, where for r equal to 4, mod tr next has become equal to previous. But for r less than 4, this is r less than 4, this is r less than 4. What is it that we have? R less than, yeah, that means for up to r equal to 3, this is r equal to 3. What is it that we have? Next term larger than the previous term. That means this greater than this, greater than this. Yes or no? No? For r equal to 4, the equality has occurred, causing mod t4 to be the same as mod t5. But prior to this, the equality had no scene. Therefore, the terms were continuously increasing. Mod tr plus 1 must have been greater than mod tr up to this point. And at this point, mod tr plus 1 became equal to mod tr. And after this, it must be decreasing only. See, up to this point, it has been increasing. And after this point, it has to be decreasing. Right? Yes, sir. So after this point, mod t5 is greater than mod t6, is greater than mod t7, and so on and so forth. Can this be said? So numerically, which is the greatest term? The fourth term and the fifth term are numerically the greatest term, right? So what's the fourth term, for example? Fourth term is 15 c4 3 to power 11 minus 5x to the power 4. Yes, so ncr a to power n minus r, x is minus 5x here to power r, right? Isn't it? And you can plug in x equal to 1 by 5 here and take the numerical value and take the numerical value mod of that. So the minus gets, isn't it? The mod of this will be numerically the largest, and the mod of t4 will be the same as mod of t5. So no matter which one you at x equal to 1 by 5. So no matter which one you compute, you will get the same value. You will get the same value, right? Isn't it? Confused? So this is an important variety, and you must take proper notice of this. Okay. Now let me introduce another notation to you. Huh? Oh, T4. I'm so sorry. Thank you. T4 is T3 plus 1, R is 3 here. I'm so sorry, fix this. 15C3, A to power n minus R, x to power R. Thank you so much. Yeah. Right? Now, let me introduce another notation to you, but this much has been registered by all, right? How to find numerically the greatest term in a binomial expansion for a certain value of a and for a certain value of x, right? Now, a notation. Let me look at a notation. See, we've learnt this single summation notation. Summation I equal to 1 to n, we've learnt as like a1 plus a2 plus an, right? That's a single summation that we have learned, right? Let me teach you the double summation notation now. Let me teach you the double summation notation, okay? You understand this, right? This we've learned before. Let's look at a variation around this, a double summation notation. Clear? Aij, double summation Aij, where I greater than or equal to 0, less than j, less than or equal to n. Let me teach you how to deal with something like this. Double summation Aij, I greater than or equal to 0, less than j, less than or equal to n. Let's examine this. Let's examine this. Now, the way to look at it is, there are two running variables here, I and j. I can start all the way from 0. Its pair j at any given instant would be larger than I, right? So, if I is 0, j will take what all values? J will take a value 1, 2, 3 and go all the way to n. Do you realize that? Say if I is 0, the values assumed by j would always greater than I will start from 1 only. J will take values like 1, 2, 3 all the way to n, right? Then if I assumes a value 1, then j will start from 2 onwards. J will assume values like 2, 3 all the way to n. I is 2, then j will start from 3, 4 all the way to n. Going this way, I is n minus 1, then what's the only value that j can take? N. And what if I is n? Not possible. I is n is not possible, because then you can't choose a value of j bigger than I. J bigger than I then cannot be selected. So I will take values all the way from 0 to n minus 1. And for any given I, j will start from 1 more than I and go all the way to the rightmost extremity, right? Now, this therefore would mean the following. So I can think of n rows of summation I equal to 0 to n minus 1 is n rows. A row dedicated to I equal to 0, then a row dedicated to I equal to 1, and then a row dedicated to I equal to 2, and then a row dedicated to I equal to n minus 1. So then let me start with the row that starts with I equal to 0. I equal to 0 means a 0, j will be 1. I is 0, j can be 2. I is 0, j can be 3. I is 0, j can be 4. I is 0, j can be n, right? Isn't it? That's the first row. Plus. Now plus. This is for I equal to 0. Now I equal to 1. When I is 1, j will then start from 2 onwards. So then when I is 1, j will be 2. When I is 1, j could also be 3. When I is 1, j could also be 4. When I is 1, j could also be n. This row dedicated to I equal to 1. Similarly, the next row plus dedicated to I equal to 2. So when I is 2, j can be 3. When I is 2, j can be 4. When I is 2, j can be n, right? This row dedicated to I equal to 2 and j going from 3 all the way to n. And eventually the last row, which is I equal to n minus 1 and j is n. So when I is n minus 1, j is n. When I is n minus 1, j is n, right? The first row I equal to 0, the second row I equal to 1, the third row I equal to 2, the fourth row I equal to, and the last row, nth row I equal to n minus 1. Yes or no? Do you understand this clearly? Right? Now, can I wipe this off? Suppose I had the following summation. Okay, the following double summation. The CIs are the binomial coefficients, say. Let's get to business. CIs are the binomial coefficients. I want to find double summation I greater than or equal to 0, less than j, less than or equal to n. This S. Okay. Of what? Of CI, Cj, where a CI would really mean NCI, is synonymous with NCI, the binomial coefficient. All right. Let me seek to deal with S. Let me seek to deal with S then, right? So then in this, again, I'll have n rows. The first row dedicated to I equal to 0, j going from 1 to n. The second row dedicated to I equal to 1 and j going from all the way to 2 to n. Then I equal to 2, j running from 3 to n. I equal to n minus 1, j having a unique value n, right? So then this is like C naught C1 I equal to 0, C1 C naught C2 I equal to 0, j equal to 1, I equal to 0, j equal to 2. This is all I equal to 0 and j going from 1 to n. Yes or no? Right, that's the first row for I equal to 0. Then the next row, I equal to 1. So I equal to 1, j will be 2. I equal to 1, j could also be 3. I equal to 1, j could also be 4. I equal to 1, j could also be n. Yes or no? Then the third row for I equal to 2. I equal to 2. So when I is 2, j can be 3. When I is 2, j could also be 4. When I is 2, j could also be n. Yes or no? And then going this way up to the last row, which is for I equal to n minus 1. So when I is n minus 1, the only value j could assume is n. So double summation Ci Cj I running from I greater than or equal to 0, less than j, less than or equal to n means this kind of a summation, right? Now in this summation, one peculiarity that you see is this could be looked upon. See, if I had these numbers C0, C1, C2, Cn, if I had these numbers, right, do you realize that every Ci Cj has appeared only once? That means, see, C0, C1 has appeared only once. C0, C2 in this entire business has appeared only once. C0, C3 has appeared only once. C2, C4 will appear only once, right? And all pairs are appearing. I mean, if you think of, randomly think of a pair, say C5, C8, that has necessarily appeared. That is for I equal to 5 and going 8 logs down, right? See, that means every pair in this sum has appeared. This could be looked upon as sum of the product of these numbers. These are a certain set of numbers. This S should be looked upon as sum of the product of these numbers taken 2 at a time. Sum of what? This is a sum. S is the sum of the product of these numbers taking 2 at a time. Yes or no? Right? The order is not important. C0, C1 is just one term. You won't have C1, C0 appearing again in this, right? Yes or no? From combinatorics, how many terms will appear in this? Taken, if there are n, if you take 2 at a time, then how many such pairs will be there? NC2, absolutely. Yes or no? There would be NC2. How many terms are these then? NC2. NC2 terms. Yes or no? Sounds good, right? Now now realize that I need to find a place where this will appear. This S, I need to find where will this S appear. This is sum of the product of these numbers. This is sum of the product of these numbers taken 2 at a time, right? Yes, yes, I want to figure out physically where will this appear. This will appear in the following. Very good. C0 plus C1 plus C2 plus C3 plus Cn whole square. If I do, then what you will get is, you will get two kinds of terms. You will have like these square terms, C0 squared plus C1 squared plus C2 squared plus Cn squared kind of terms, plus twice S, sum of the product taken 2 at a time, is what you will get. See, you will have like a C0 C1 coming your way, C1 C2 coming your way, isn't it? And isn't it? This will give me S, twice S, all of these, where S will be this. Yes or no? Right? So if I expand this, then the S will appear here. The S will appear here, twice S. This S would be C0 C1 plus C1 C2 plus C2 C1 C3 plus all such products will appear. All pairs will appear in this S exactly once, and every pair must appear. Every pair must appear. What do you say? Are you confused? No? So this S, which is sum of the product taken 2 at a time, and by the way, you know, this is just to stand corrected in one way. C0, C1, C2, Cn are how many numbers? They are actually n plus 1 numbers. So the number of terms here will not be nC2, but would be n plus 1 C2. The number of terms here will not be nC2, but actually n plus 1 C2, because there are n plus 1 of these numbers taking 2 at a time. The number of pairs produced is going to be n plus 1 C2, right? So this would be n plus 1 C2 terms. How twice? देखो, C0 plus C1 plus C2 into C0. Suppose n is 3. तो देखो, C0 C1 and then C1 C0, twice C0 C1, isn't it? See, you have a term like C0 C1 coming and a term like C1 C0 coming, which is like twice C0 C1, isn't it? That's why. Yeah, you see there are n terms here, there are n minus 1 terms here, so n plus n minus 1 plus n minus 2 plus n minus 3 up to 1. So 1 plus 2 plus 3 up to n, which is n into n plus 1 by 2, which is the same as n plus 1 C2. See, one term here, then there will be 2 terms, then there will be 3 terms, then there will be 4 terms, and there will be n plus 1 n terms here. So sum of the first n natural numbers, which is n into n plus 1 by 2, which is also the same as n plus 1 C2. Number of such pairs is going to be n plus 1 C2. Clear? Now, so I hope you are all mentally clear about where exactly this sum of the product taken 2 at a time appears, right? Confused kya? Nahi na? Now, let me find out the value of S. Let's find out the value of S. The value of S is going to be, see, C0 plus C1 plus C2 plus Cn whole square is summation CR squared, R equal to 0 all the way to n, that is C0 squared plus C1 squared plus C2 squared plus Cn squared plus twice S. Now C0 plus C1 plus C2 plus Cn is what? 2 to the power n. So this will become 2 to the power 2n. Now this one we found out in the last class, 2n Cn, this is 2n Cn. Remember that? So this is 2n Cn. I told you, you must remember this result, and that will be twice the required S. Divide by 2 will give you S, sum of the product taken 2 at a time of these binomial coefficients. Is that okay or not okay? You know? Confused? No, no? Make sure you understand this notation right here, right now in the class, because books just assume you know this and they take no effort to explain it to you. Schools, it's out of syllabus. That's the fair and final answer that they'll give you. So it's easy, so and very manageable, so make sure you understand it right now, right here. If you have doubts, please ask me. No, no? Now, can I wipe this off? Can I wipe this off? Let me give you another summation. Another summation, say double summation Ci plus Cj whole square I greater than or equal to 0, less than j, less than or equal to n. Let's figure this out. Right? So first of all, systematically spread these terms out. Very systematically, let's spread these terms out. Okay? The first row dedicated to I equal to 0, the second row for I equal to 1, I equal to 2, I equal to n minus 1. These would be our different rows. Okay? So the first row is like a C0 plus C1 whole square, I equal to 0, j equal to 1, I equal to 0, j equal to 2, I equal to 0, j equal to 3, I equal to 0, j equal to 4. Going this way, I equal to 0, j equal to n. Right? That's the summation for I equal to 0. Then for I equal to 1, let me look at I equal to 1, the second row. So C1, j will then start with 2, whole squared, sorry. This for I equal to 1, right? Then the next one would be I equal to 2. Whole square, right? And then the last row would be for I equal to n minus 1 precisely. Right? Let me call this S1. Let me call this summation S1. I need to find S1. See, realize when I expand this, it will give me C0 squared plus C1 squared plus 2 C0 C1, C0 squared plus C2 squared plus 2 C0 C2, etc. Now there is a C0 square source from here, 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 a C0 square source from here. That is n times C0 squared. So this is n times C0 squared in the first place plus, look, C1 squared. C1 squared has appeared n minus 1 times here and once here. So n times C1 squared. C2 squared has appeared once here, and n minus 2 times here. So n times C2 squared. And now you can almost conclude that this will be terms of this kind, where the Ci squares are all taken care of. Now what you are left with? Absolutely, the middle terms 2 C0 C1, C0 C2 plus C0 C3 plus C0 C4 plus C0 Cn plus C1 C2, C1 C3, C1 C4, C1 Cn. All pairs are appearing now. That means the next set of terms would be twice the sum of the product taken 2 at a time. The next would be sum of the product taken 2 at a time, right? And we have found the value of 2s already. And this we know, C0 squared plus C1 squared plus C2 squared plus Cn squared is 2n Cn. And S also we have figured out, sum of the product taken 2 at a time. So we know S1, we precisely know S1. Is that all right or not all right? Have I confused you? No? Can I wipe this off? Can I wipe this off? Hmm? Now, let me teach you something about an expression which is of great importance, not just in regular algebra, but down the line when we learn calculus, this expression would be of consequence. An expression, to begin with, we'll talk of n to be a natural number, and we'll seek to deal with an expression a n, which is 1 plus 1 by n whole to power n, an expression of this kind, 1 plus 1 by n whole to power n. Now, n is a natural number. If I expand this binomially, how many terms will I have? N plus 1 terms, right? And 1 plus x power n, like I told you in raw form, is 1 plus nx plus n into n minus 1 by 2 factorial x squared plus n into n minus 1 into n minus 2 by 3 factorial x cube up to n plus 1 terms, right? So let me give it a raw form. Let me expand it in the raw format. This 1 plus 1 by n whole to power n. Let's do that, all right? One plus n into 1 by n nx. X is 1 by n, right? X is 1 by n in this case. N into n minus 1 by 2 factorial x, which is 1 by n whole square, right? N into n minus 1 into n minus 2 by 3 factorial cubed up to how many terms? N plus 1 terms. Yes or no? Now, very clearly, this is 1 plus 1, 2, plus some more positive numbers. It's 1 plus 1, 2, plus some more positive numbers. So, n for sure will always be greater than 2 for any value of n, right? An is always greater than 2 for any value of n. You can readily see, right? Now, this I could write as 1 plus 1 plus if I divide by n squared, this n will get cancelled. This will become 1 minus 1 by n, right? So, this will become 1 by 2 factorial 1 minus 1 by n, right? This will become 1 by 3 factorial n cube. 1 n will cancel this n. This will become 1 minus 1 by n into 1 minus 2 by n, right? 1 by 4 factorial, similarly 1 minus 1 by n into 1 minus 2 by n into 1 minus 3 by n up to n plus 1 terms. Yes or no? Now, realize that as n increases, 1 by n will decrease, but the power will increase. So, we need to figure out whether, so it's dubious to figure out whether an is going to increase or decrease. See, there are two opposing forces. When I increase n, then 1 by n is decreasing. Hey, but the power is increasing. So I need to see whether an is increasing, or because part of an is decreasing, part of an is causing it to increase. But whether there is a net increase in an or there is a decrease in an as n increases, I need to judge that. You know what my intention is? Okay. Now, as n increases, then the number of terms will increase? Yes or no? As n increases, the number of terms will increase. In the expansion will increase, right? Now the value of each term. See, as n increases, 1 by n will decrease, right? So 1 minus 1 by n will increase, yes or no? If 1 by n decreases, 1 minus 1 by n will increase, isn't it? As n increases, 1 by n decreases, but 1 minus 1 by n will increase, isn't it? 1 minus 2 by n will increase, 1 minus 3 by n will increase, yes or no? Now, which means as n increases, this increases, this increases, this increases, this increases, this increases, this increases. The value of each term is increasing, and also the number of terms is increasing, right? The value of each term is increasing, and so also is the number of terms. So that means n must be increasing as n is increasing. If the value of each term is increasing and also the number of terms is increasing as n increases, then n must be increasing as n increases. Yes or no? Yes. Nahi. Wapas bole? All that I am saying is, see, what am I trying to do? I am trying to see what happens to an when I go from n equal to 3 to n equal to 4, say, or n equal to 3 to n equal to 10, whether a3 is bigger or a10 is bigger. I want to figure that out, right? So, see, if you increase n, the number of terms, which is n plus 1, is increasing. Now, what about the value of each term? 1 by n is 1 by n will decrease, but 1 minus 1 by n will increase. So this term increases as n increases. This term will also increase as n increases. So value of each term is increasing, and also the total number of terms is increasing. So n must be increasing, isn't it? If you increase n, then the value of every term is increasing and the number of terms is also increasing. So n is increasing. Have I confused you? No. So as n increases, an also increases. Yes or no? So an plus 1 will always be bigger than an plus 2 will always be bigger than an plus 1, and so on and so forth. Clear? Now, so this is an important thing to register, right? As n increases, the value of this expression will increase. Okay, even though this is decreasing, the power is increasing, but the power prevails. The power is all powerful here. Okay, now another remark on this. See, 1 minus 1 by n is less than 1, of course also greater than 0. 1 minus 2 by n is also less than 1 and greater than 0. 1 minus 3 by n is also less than 1 and greater than 0. So 1 minus 1 by n into this will also be less than 1, greater than 0. This into this will also be less than 1 and greater than 0, and so on and so forth, right? So can I say that this is a number less than 1? Therefore this will be less than 1 by 2 factorial, yes or no? I mean 1 by 2 factorial, can I not say into 1 minus 1 by n, can I not say will be less than 1 by 2 factorial? Because this is less than 1. If you multiply a number with a number less than 1, then you will get a smaller number. So this will be smaller than this, isn't it? Similarly, can I not say that this is less than 1, this is less than 1, so this whole thing will be less than 1 by 3 factorial, this whole thing will be less than 1 by 4 factorial. All of that could be said, right? Which means this an this is less than 1 plus 1 plus 1 by 2 factorial plus 1 by 3 factorial plus 1 by 4 factorial up to n plus 1 terms? Is that fine or not? Can this be said? Now, okay, 1 by 2 factorial is less than or equal to 1 by 2. Is it true or false? Tell me. Is this statement true or false? Can I ask you a question? And don't take offense to this. It's just with a... Okay, I'll ask you a fresh question. No offense though, okay? You are a man or a donkey. Is it true or false? I make a statement, you are a man or a donkey. Is that true or false? It's a true statement, isn't it? Because if even one is true, then the statement is true. Right? Isn't it? Our friend there has 20 or more kids. So even if he has 30 kids, the statement will be true. Right? Okay. So this is true. Right? So this is true. Now tell me, 1 by 3 factorial, which is 1 into 2 into 3, that's 1 by 3 factorial. Right? Can I say it's less than 1 by 2 squared? Because see, this is, isn't it? 1 by 4 factorial, which is like 1 by 1 into 2 into 3 into 4 would be less than 1 by 2 cube. Can this be said? Isn't it? Huh? That means this is less than 1 plus 1 plus 1 by 2 plus 1 by 2 squared plus 1 by 2 cubed up to n plus 1 terms. Right? 1 by 2 factorial say equal to 1 by 2, up to this equal. But 1 by 3 factorial is less than 1 by 2 factorial, 2 squared. 1 by 4 factorial will be less than 1 by 2 cube. 1 by 5 factorial will be less than 1 by 2 to the power 4 and so on and so forth, isn't it? So this whole thing, term by term, is less than this thing. Clear? Can I say that this in turn is less than 1 plus 1 plus 1 by 2 plus 1 by 2 squared plus 1 by 2 cube plus up to infinity? Now, whether you add terms up to n plus 1 or you add terms up to infinity, which will be more? If all up to infinity, isn't it? So this will be more than this. You are adding terms up to infinity, whereas in this case you are adding terms up to n plus 1. So this will be more because all terms are positive, is it not? Yes, the reason I convert this because this is an infinite GP series with common ratio half, right? So then an less than this, an less than this. So an less than 1 plus r squared plus r cubed, which is 1 plus 1 by 1 minus r. 1 plus, now add this GP series, 1 plus r squared plus r cube, 1 by 1 minus half, isn't it? That means an can never exceed 3, an can never exceed 3, right? So as you go on increasing n increases, but it never goes past 3, right? It will always stay bounded between 2 and 3. That's an important fact to reckon. Okay? So, so 1, as n increases, an increases. As n increases, an increases. 2, an will always lie between 2 and 3. An is bounded. An therefore is bounded. No, it will never become equal to 3. Huh?
Because when you have 1, for example, like 1 plus 1 by 1 to the power 1, it's equal to 2, right?
Yes, it could, oh, you mean to say this could be equal to 2. Yeah. For n equal to 1, what he's saying is it would be equal to 2. Yeah, absolutely. An greater than or equal to 2, it could be equal to 2, greater than or equal to 2, but less than 3. Never goes past 3. In fact, it never becomes equal to 3 also. In fact, as n tends to infinity, we will be able to show down the line that this will be e, the exponent, right? It will be equal to e as n tends to infinity. This will become e. It will be an irrational number. Forget all of it right now. But for the time being, if you've registered this, then that's good enough, right? Now, an important consequence of this. I hope it's all going smoothly into you right now, right? See, an is always less than 3 for any n, right? Now, if I select a value of n greater than or equal to 3, I select a natural number n equal to 10, say, then which will be greater? An will be greater or n will be greater? N will be greater, isn't it?
Yes,
because n, no matter what n I select, will always be less than 3. But if I select a n greater than or equal to 3, that means I could have selected n equal to 3, 4, 5, 6. For any n 3 or more, an will not exceed n, because n is less than 3 and this is greater than 3, right? So then for n greater than or equal to 3, I can say that an must be less than n. Why? Because this is less than 3 and this is greater than or equal to 3, isn't it? So an will be less than n for n greater than or equal to 3. Sounds good? Which means, what is an? An is 1 plus 1 by n to power n, less than n for n greater than or equal to 3, right? This would mean n plus 1 to power n less than n to power n plus 1 for n greater than or equal to 3, right? N plus 1 to power n to power n into n, that's n to power n plus 1, right? Which means this is an important result. N plus 1 to power n greater than n to power n plus 1 for n greater than or equal to 3. Sorry, less than n to power n plus 1 for n greater than or equal to 3. Which means, if someone says 101 to the power 100 or 100 to power 101, which is more? The one that has a larger power, will be more. 16 to power 15 will be more, or 15 to power 16 would be more? 15 to power 16 would be more, right? So useful little thing. N to power n plus 1 always greater than n plus 1 to power n, right? Can I wipe this off? Wipe this off? Now, another variety which I want to introduce, and let me use a problem to explain that concept to you. Refer to the sheet, Binomial Basics 2 part 1. which says show that the integer part of 5 plus 2 root 6 whole to power n is odd. We want to show that the integer part of 5 plus 2 root 6 to power n is odd. Let's figure this out, what it really means first. Let's understand what it means. See, when I give it a value of n, say, n equal to 200, say for example, and find the value of this 5 plus 2 root 6 whole to power 200. There is a value of this, it will have a certain value, right? And this is an irrational number, it's going to have a non-integer value. It will have a non-integer value, right? Say for n equal to 100, say 5 plus 2 root 6 whole to power 100. Okay. Now you can use your calculators to find this, don't waste your time though. Then there will be something after the decimal and there will be something before the decimal if you found the value of this, right? Something before the decimal is the integer part of it, something after the decimal is the fractional part of it. So it will be I point f. F could be 0.016411, etc. Right? This f in this case will be a fractional part, always greater than 0 but less than 1. Right? So this could always be written as an integer plus a fraction, isn't it? This is integer plus a fraction. I point f is I plus f, isn't it? Isn't it? So I is an integer, f is a fraction lying between 0 and 1. Yes or no? Yes, sir. Now what we want to establish is that no matter what n I supply, this I will always be an odd number. This I will always be an odd number, that's guaranteed. See, for example, you know, if you put n equal to 1, this will be like 4 point something, isn't it? This will be 4 point something plus 5, so this whole thing will be 9 point something. 9 is odd, isn't it? So the integer part of this is odd, and so on and so forth. You'll always be, for any n, the integer part of this obtained is going to be odd. That's what we want to establish. Now, the tool that we are going to deploy to establish that is binomial theorem. Let's see how we can put our acts together and use binomial theorem effectively to establish this proposition. Okay? See, 5 plus 2 root 6 whole to power n will have an integer part I plus a fractional part f, where f will be greater than 0 and less than 1. And we want to show that this I will be odd. Okay. Now if I choose to expand this binomially, it's going to be 5 to power n first term plus nc1 5 to power n minus 1 2 root 6 plus nc2 5 to power n minus 2 2 root 6 whole square, nc3 5 to power n minus 3 2 root 6 whole cubed, etc. up to n plus 1 terms in the expansion, right? Now, I claim 5 minus 2 root 6 into 5 plus 2 root 6 is equal to 1. Obviously, what's about a claim here? Right? So 5 minus 2 root 6 is like a 1 by 5 plus 2 root 6? Yes or no? And this is clearly less than 1. Now, the product of these two numbers is positive, and this is positive, so this must also be positive. So this is greater than 0. So 5 minus 2 root 6, without doing any calculations, is less than 1 but greater than 0. Right? 5 minus 2 root 6 is always greater than 0 but less than 1. Now if there is a number that lies between 0 and 1, if you raise it to power 5000, it will still lie between 0 and 1. It will keep decreasing as n is increasing. Right? So 5 minus 2 root 6 to power n will always be a number lying between 0 and 1. So this number 5 minus 2 root 6 to power n has 0 integer part and f prime the fractional part. F prime is the fractional part of this to power n. Right? Yes or no? Yeah, why not? You understand this? So do you understand 5 minus 2 root 6 less than 1 greater than 0? Suppose 5 minus, there is a number less than 1 and greater than 0, 0.3. If you raise it to a power 5000, it will still lie between 0 and 1. Na? So raise it to power n, it will still lie between 0 and 1. Right? So 5 minus 2 root 6 to power n has 0 as its integer part and f prime as its fractional part. F prime will be greater than 0 and less than 1. Right? 5 minus 2 root 6 to power n will simply be f prime, where f prime would be a number lying between 0 and 1. If there is a number 0.3, what is its integer part? 0. Isn't it? If there is a number lying between 0 and 1, its integer part has to be 0, isn't it? Clear? No, f prime is just a number lying between 0 and 1, isn't it? See, okay, 5 minus 2, please, 5 minus 2 root 6 to power n is less than 1 and greater than 0. So it's just, its integer part is 0, isn't it? And it's just a fraction, you call that fraction f prime. This is just a fraction and you call that fraction f prime. Its integer part, it will have no integer part, its integer part is 0 in fact. So it will be 0 plus f prime. Right? Now, to expand this, I just go here and replace, wherever 2 root 6 appears, I replace that by minus 2 root 6, I'll get the expansion of this. To get the expansion of this, I come down here and replace the 2 root 6 by minus 2 root 6, wherever 2 root 6 appears. Right? So 5 minus 2 root 6 to power n is 5 to power n. This 2 root 6 replaced by minus 2 root 6. So that will be minus nc1, 5 to power n minus 1, 2 root 6. This 2 root 6 replaced by minus 2 root 6 will give me the same value. Right? So plus nc2, 5 to power n minus 2, 2 root 6 whole squared. This 2 root 6 replaced by minus 2 root 6, you will have a minus sign appearing here. So minus nc3, 5 to power n minus 3, 2 root 6 whole cubed. Yes or no? Now, what are the numbers that are hurting here? The irrational numbers. See this 2 root 6, because this will be non-integral. 2 root 6 whole cube, this is non-integral, it's hurting. 2 root 6 whole to power 5 will be hurting, because even powers of 2 root 6 are alright, because they are integers, not a problem. But odd powers of 2 root 6 are terribly irrational, right? And we want to weed them away to begin with. The way to weed them away is, if I add these two, then the odd powers of 2 root 6 will go into oblivion. right? So let me vertically add I plus f prime. What I'm left with is simply the following. See, in certain cases I need to add, in certain cases I need to subtract. The whole idea of adding or subtracting will depend on what would cause the irrational parts to get weeded away, so that the right hand side is an integer easier to deal with, right? So now the right hand side is twice 5 to power n plus nc2 5 to power n minus 2 2 root 6 whole squared nc4 5 to power n minus 4 2 root 6 whole to power 4, etc. Right? And this is an integer. Integer into integer into integer, integer. Integer into integer into integer, integer. The whole thing inside the parenthesis is an integer. The right hand side therefore is true into an integer, therefore it's an even integer. The right hand side therefore is an even integer. This is an even integer. So we have I plus f prime. An even integer? No, the problem is not yet solved. Just a few closing remarks. Now, hey, look. This is an integer for sure, right? I is an integer. Therefore, f plus f prime must be an integer. Yes or no? Only then they can add up to an integer. Yes, absolutely. See, I is an integer. F plus f prime also must be an integer, so that their sum is an integer, isn't it? But f and f prime are two numbers lying between 0 and 1. What's the only integer they could add up to? 1. The only integer two fractional parts could add up to is 1, isn't it? So f plus f prime, for it to be an integer, the only possibility is f plus f prime equal to 1. That's the only integer two fractions can add up to, isn't it? So f plus f prime is 1, right? Therefore I is even integer minus 1, which is an odd integer. So I, the integer part of this, will always be odd. I, the integer part of this, will always be odd, right? So look at the prowess of binomial theorem. So powerful a tool. It's not without reason that you study so much of binomial theorem, right? Now, just to get hands on with another problem. Can I wipe this off? Part 2. We want to show that the integer part of 5 root 5 plus 11 to the power 2n plus 1 is even, right? We want to show that the integer part of 5 root 5 plus 11 to power 2n plus 1 is even. Okay. Now, like before, a very routine thing. For any value of n, this will be I point f. I is an integer, f is a number lying between 0 and 1. So this will be I plus f. I plus f, that will be I point f kind of a thing, isn't it? So 5 root 5 plus 11 to power 2n plus 1 is going to have an integer part, and after the decimals it will have a fractional part. F is a number lying between 0 and 1, right? I expand this binomially. Let me expand this binomially, right? So that's like 5 root 5 whole to power 2n plus 1 plus 2n plus 1 c1 5 root 5 whole to power 2n, 11 C2, 5 root 5, 11 squared, 2n plus 1 C3, 5 root 5 whole to power 2n minus 2, 11 cubed, up to 2n plus 2 terms, up to 2n plus 2 terms in the expansion of this, right? Now, look at 5 root 5 minus 11 into 5 root 5 plus 11. 125 minus 121, that is 4. This is positive. The product is positive, so 5 root 5 minus 11 must be positive. And 5 root 5 plus minus 11 is 4. 5 root 5 minus 11 is 4 divided by 5 root 5 plus 11. So, which is less than 1? So, this is always less than 1, right? Greater than 0, but less than 1. So, if you raise it to any power, that will also lie between 0 and 1. So, if you raise it to a power 2n plus 1, it will still lie between 0 and 1. That means if it's a number lying between 0 and 1 for any n, it must be purely fractional. That means its integer part will be 0. That means, can I not say 5 root 5 minus 11 to power 2n plus 1 will simply be f prime, where f prime is just a number lying between 0 and 1. Is that okay or not okay so far? Now, can I wipe this off? Five root 5 minus 11 to power 2n plus 1 is simply f prime, where f prime is less than 1 and greater than 0, right? So, what am I going to do in this? I just replace by 11 by minus 11 in the entire scheme of things here. I replace 11 by minus 11. When I do that, then I get 5 root 5 to power 2n plus 1 minus, replace 11 by minus 11, 2n plus 1 C1, 5 root 5 to power 2n into 11 plus 2n plus 1 C2, 5 root 5 to power 2n minus 1 into 11 squared minus so on and so forth. This is what I get, replacing 11 by minus 11, terms alternating between positive and negative terms, right? Hey, what terms do you not like here? The first term you don't like, but you like this term because 5 root 5 to an even power will be an integer, right? You don't like this term, 5 root 5 to an odd, terribly odd, right? Non-integer, integer, and so on and so forth. Now, so therefore you want to dump these terms, first term, third term, fifth term, seventh term you want to dump. So whether you want to add or subtract, subtract to dump the irrational numbers appearing in this expansion, right? So subtract I plus f minus f prime, I plus f minus f prime, right? So twice this, twice C3, and so on and so forth. So twice 2n plus 1 C1, 5 root 5 to power 2n into 11. This is an integer, and then plus 2n plus 1 C3, 5 root 5 whole to power 2n minus 2 into 11 cubed, and so on and so forth. This is an integer, 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 integer. So this is twice an integer. So an even integer. So I plus f minus f prime is an even integer. I plus f minus f prime is an even integer, right? Now I is, therefore this must be an integer for sure. So I is an integer. So f minus f prime must also be an integer, right? Now what's the only integer which is the difference of two fractions? 0. So very good. F minus f prime therefore must be 0. And if f minus f prime is 0, then I must be an even integer. Hey, one thing then. Since f is f prime, the fractional part of this is actually this. That's what it means. See, since f is f prime, the fractional part of this is actually 5 root 5 minus 11 to power 2n plus 1. Yes or no? Right? This is what you do. Clear? Now, let me explain another variation. Sometimes they'll ask you to find, say, refer to problem 10 of the sheet. Find the coefficient of x power 50 in the expression. Let me know if I can wipe this off and if you are done with this. Problem 10, which is like, find the coefficient of x power 50 in 1 plus x to power 1000 plus 2x into 1 plus x to power 999 plus 3x squared into 1 plus x to power 998 we want to find the coefficient of x power 50 in this expansion. Okay, we want to be able to find the coefficient of x power 50 in this expansion. Okay, see, let me find this sum s, huh? And then 2 into 3 etc, all of that. So yeah, in this case what we'll do is, that's one way to do it. First of all, let me add this series if possible. What kind of a series is this? Arithmetico-geometric progression. See, 1, 2, 3, 1001 are an arithmetic progression, whereas 1 plus x to power 1000, x into 1 plus x to power 999 and x squared into 1 plus x power 998 up to x to power 1000, right? This is a GP series. This is a GP series with common ratio x by 1 plus x. This is a GP series with common ratio x by 1 plus x. Do you see that? To get any term, you multiply the previous term with x by 1 plus x. X by 1 plus x. This is what transpires. Right? So it's an arithmetico-geometric progression. It's an arithmetico-geometric progression. Partially 1, 2, 3 AP, and then this second constituents will be all GP. Alright. Now, how many terms are these? 1, 2, 3 up to 1001. 1001 terms, isn't it? Now, what we do here is, to deal with this arithmetico-geometric progression, if R is the common ratio, x by 1 plus x is the common ratio of the GP part, then we multiply this with R and shift 1 unit to the right. That's what we do, if you remember. We multiply S with the common ratio R and shift the whole thing 1 unit to the right. That was a routine procedure. You've forgotten, you need a test in progressions. So I do the following: R, which is x by 1 plus x, into S. I multiply all terms with this and shift the whole thing 1 unit to the right. So when I do that with this, I get x by x into 1 plus x to power 999. I've multiplied this with this and shifted 1 unit to the right. When I do to this, then I get 2x squared into 1 plus x to power 998. And I keep doing this, and the whole sequence would move by 1 unit to the right. Huh? Mobile ta. I multiply this by x and divide by 1 plus x. Sounds good? Right? No, I was not that vocal. Right? So then realize up to this point there'll be 1001 pairs, right? First pair, second pair, third pair, 1001 pairs, and then this would be a lone one, right? Let me subtract as we've done conventionally. When I subtract, s into 1 minus x by 1 plus x. Will be 1 plus x to power 1000, right? By minus x into 1 plus x to power 999 plus x square into 1 plus x to power 998. I take up to this point, that means up to 1001 terms, and minus 1001 x to power 1001 divided by 1 plus x. What about this? Yes or no? Now up to this 1001 terms, when I have paired, this entire thing is now a pure GP series with common ratio x by 1 plus x. Up to 1001 terms, we simply have a GP series with common ratio x by 1 plus x, first term being equal to this, number of terms being 1001. So sum of 1001 terms of a GP series would be A, which is this, into R, which is x into x by 1 plus x, to power n, which is 1001, minus 1 divided by R minus 1. Yes or no? Right? So this is A into 1 minus R, which is to power n, n is 1001, divided by 1 minus R, right? That's as far as the GP part is concerned. A into 1 minus R to power n divided by 1 minus R. Weber. Huh? And minus, this is unaccounted for, set aside, minus 1001 x to power 1001 divided by 1 plus x. Huh? Oh, x by 1 plus x. Oh, this one, right? Yeah. You're right. Right, Prakhar. This would be all 1002. X by 1 plus x. Yes, absolutely. Right. Now let me simplify this. Let me simplify matters here. Okay. Can I wipe this off? See, the last term was 1001 x to power 1001, right? No, it was 1001, isn't it? 1001. So when this was multiplied with x by 1 plus x, it will become x to power 1002, and it would have got shifted 1 unit to the right. Thanks. Now this will become 1 by 1 plus x, isn't it? 1 by 1 plus x is what becomes of it. right? And when this goes in the numerator, this will become 1001, right? Isn't it? Now when I multiply it throughout, this s will be 1 by 1 plus x equal to 1 plus x to the power 1001 into this minus x to the power 1001, right, minus 1001 x to the power 1002 divided by 1 plus x, that's s. See, till this point there is no binomial, it's only what we did in the past, arithmetico-geometric progression, right? Now to find s, the big expression s then is like a 1 plus x to the power 1002 minus x to the power 1001 into 1 plus x minus 1001 x to the power 1002. Yes or no? That's the summation s. Clear? Now can I just remove this? Now will there be any appearance of x power 50 in this? There is no x power 50 in this. So in this whole thing x power 50 will appear only here, and therefore coefficient of x power 50 in the whole thing will be coefficient of x power 50 here. Yes or no? So coefficient of x power 50 in s is actually the same as coefficient of x power 50 in 1 plus x to the power 1002, right? And the coefficient of x power 50 in this is actually 1002 c 50. Coefficient of x power r is going to be NCR. That's going to be the coefficient of x power 50. Got me? What is the problem? In the problem we are seeking coefficient of x power 50 in s. Is there any x power 50 appearing here? This is x power 1001 into 1, x power 1002. Is there any x power 50 appearing here? So that means x power 50 in the whole thing will appear only here, isn't it? So coefficient of x power 50 in the whole thing is actually coefficient of x power 50 in this only, and coefficient of x power 50 in s, this whole thing is actually coefficient of x power 50 in 1 plus x to the power 1002, which would be 1002 c 50. Now no, you started from term by term, we could have proceeded, and then using properties of binomial theorem we could have used that, but it will be a lot more complicated than doing this, right? So this is the best thing. Otherwise you took for every term you found the coefficient of x power 50 and added term by term, but that's going to be very elaborate, right? Now there is yet another variety I want you to get acclimatized to. Say problem 11 of this sheet. We want to find which is greater, 1000 to power 50 plus 99 to power 50 or 1001 to power 50. We want to figure out which of the two is larger, 100 to power 50 plus 99 to power 50 or 101 to power 50. What was I saying, 1000? Sorry. 100 to power 50 plus 99 to power 50 or 101 to power 50, which is larger, we need to figure out. Okay, we do not know. Here's a question mark here. Okay, so can I say 100 to power 50 question mark 101 to power 50 minus 99 to power 50? Can I say this? This question mark could be greater than, equal to, or less than, isn't it? Isn't it? Why not? This question mark could be greater than, equal to, or less than, and just transpose this. So anyways it will change sign irrespective of what this question mark is, right? Okay, so that means I'm comparing these two. Now 100 to power 50 question mark, this is 100 plus 1 to power 50 minus 100 minus 1 to power 50. Yes or no? Right hand side? Right? I expand binomially 51 terms of this and 51 terms, and you know the terms will, alternate terms will get cancelled off here. So then this right hand side is 100 to power 50 plus 50C1 100 to power 49, 50C2 100 to power 48 plus 1 kind of terms minus this 100 to power 50 minus 50C1 100 to power 49 plus, yes or no? Binomial expanding both, this is what transpires. So 100 to power 50, now we are comparing with this. Now realize that 100 to power 50 will get cancelled with 100 to power 50, 100 to power 48 will get cancelled with 100 to power 48 here. What remains is like 50C1 twice, 50C3 twice, 50C5 twice when I do this, right? So eventually 100 to power 50 I'm just comparing with twice 50C1 100 to power 49 plus 50C3 100 to power 47, right? 2 into 50 100, this is 100 to power 50 and plus some positive terms, yes or no? So we have 100 to power 50 being compared with 2 into 50 100, 100 to power 49, so that makes it 100 to power 50 plus some more positive terms. Which is bigger? This is bigger, isn't it? This is bigger, this is smaller, right? So replace the question mark with the less than sign. Replace the question mark with the less than sign. It might seem like, two terms, bada terms. One term, chota, thoda sa bada, thoda sa chota. This must be bigger. But actually this is smaller, right? The left hand side is actually smaller. Right? Huh? Right. Yeah. Don't go by your instincts. Or 8. We need to find the number of terms, in fact dissimilar terms, in the expansion of x plus y plus z whole to power 10. We want to find the number of dissimilar terms in the expansion of this. Hey, I could have expanded x plus y plus z whole to power 10 as follows. This has sum a, this has sum b. So a plus b to power 10, which would be a power 10 plus nc1 a power 9 b and so on and so forth. right? So if I expand as a plus b to power 10, I would get like a x power 10 plus 10c1 x power 9 into y plus z to power 1 plus 10c2 x power 8 into y plus z whole square, 10c3 x power 7 y plus z whole cubed, 11 such terms, right? Now up to the last term is like a 10c10 y plus z whole to power 10. That's the last term. Now the number of dissimilar terms that you see here. There is one term here, number of terms. One term here plus, see, y into this plus z into this, two terms here. When you expand y plus z whole square, there will be three terms, each multiplied by x power 8, so there will be three terms. Y plus z whole cube will be four terms, this will give me four terms. Y plus z power 10 will give me 11 terms. What is this? Sum of the first 11 natural numbers, which is 11 into 12 by 2, which is 66. 66 dissimilar terms in the expansion of this. 66 dissimilar terms in the expansion of this. Dissimilar terms. Got me? Where? There cannot be terms that are equal.